Okay. So, we already know that the length of a curve r equal to r t, where t varying in the interval a b is given by integral a to b mod of r dot dt. This fact is known to all of us. Now, what I do here is I replace the upper limit by the variable t. Okay. So, what will happen is the left hand side will become a function of t. Okay. So, this you can easily realize that in a space, if your curve is drawn like this, the point A is here and B is here. If I take the length up to certain point t, the measure of the length will be somewhere up to here. If you choose your point t to be over here, the length will be smaller, it will be something up to here. So, this length will become a function of t. Okay. So, now S becomes a function of t. It's in fact, it's an increasing function, monotonically increasing function of t. So, I can differentiate, I assume that it is differentiable. So, if I differentiate it with respect to t, so ds upon dt will be modulus of r dot, and this implies that ds upon dt whole square is equal to r dot r dot. Okay, because it will be mod of r dot square, which is r dot dot r dot. So, r dot we have seen has component dx upon dt, dy upon dt, dz upon dt. So, from here I can see that ds upon dt whole square is equal to dx upon dt whole square plus dy upon dt whole square plus dz upon dt whole square. Or in short, I can say in terms of differentials, I can write down ds square equal to dx square plus dy square plus dz square. All right. So, these are some important observations. Let me call this equation as that was number 1, this is number 2. And now, what you see is that S is a differentiable function of t, monotonically increasing function of t. So, S is a function of monotonically increasing function of t. So, this is monotonically increasing function, and 1 1 also. It is 1 1 also. It is 1 to 1 also. So, a 1 to 1 differentiable monotonically increasing function. And now, once S is a differentiable function, 1 to 1 function of S of t, then t should also be a differentiable monotonically increasing function of S. So, this implies that t is a monotonically increasing differentiable function of S. So, the situation is that you have your position vector r, which is a function of t, and t becomes a function of S. So, this implies that r is a function of S. So, what you get is that the position vector is a function of this S. This new variable that has emerged from here is called the natural parameter. So, I can assume that this S is a parameter which is a natural parameter for obvious reason, because parameter is not coming from an external interval, it is coming from the curve itself. So, we also call it an intrinsic parameter. So, this parameter S, this implies S is a parameter of the curve RT, this curve, okay, this is one of the curve 1, okay, known as natural parameter, known as the natural parameter. Of the curve. Natural parameter, sometime we also call it intrinsic parameter or intrinsic parameter, or some people call it arc length parameter or arc length parameter. This is the distance function, in fact, along the surface, whatever curve you, we right now we don't need it, but we will be using this formula as well as a distance function, okay. All right. Okay, so I wrote down without the parameter t, because when you will be working on a surface, you can go onto the surface. Whenever you will move on a surface, you will be moving along certain curve. So, the curve will always be there. So, why to mention the parameter all the time? Okay. All right. So, this is the natural parameter, and now we move on to some example. So, there are some examples, some simple examples. Let me start with circles. A circle for simplicity, I can consider a circle centered at the origin. So, it will look like x equal to a cos theta, y equal to a sin theta, and z equal to say 0. Okay. So, this becomes the parametric equation of a circle whose center is at the origin and radius is a. So, and the theta over here, which varies between 0 to 2 pi, becomes the generalized parameter, is the generalized parameter. Now, similarly, other conic section, all of them are in fact plane curves. So, secondly, you can consider an ellipse. For simplicity, I can assume that its center also is at the origin. So, its parametric representation will be x equal to a cos theta, y equal to b sin theta, and z equal to 0. So, once again, this is a plane curve and theta is a generalized parameter. Similarly, parabola and other, you can see that all these conic sections are parametric curves, a parabola. I can take them to be standard one. So, standard parabola in parametric form has this equation, at square and y equal to 2at, z equal to 0. So, here the parameter is t. Now, coming to some space curve, number 4, you can think of a helix, a circular helix. This is not a plane curve, this is a space curve whose parametric equation is given by x equal to a cos theta, y equal to a sin theta, and z equal to you know its shape, so but you can realize that this is a space curve essentially, and you can allow it to vary from anywhere to anywhere. So, it does not make much of a difference. So, these are some of the very well known example. You have seen their parametric equation also. All right. Okay, there are certain other how much time? Okay. So, we can stop at this point because you have to go for. Okay, all right. Okay, we stop at this point and we will continue our next lecture next time.